All right, well, hello everyone, and welcome to Saylor Academy's Bitcoin for Developers, unit number 3. You got to hear a little bit of behind the scenes because while I unmuted you, I did not mute myself. So, hello everyone, and thank you so much for joining us. I hope if you have not seen the previous 2 videos in this series, you could check them out in the playlist below. And also, just to mention, this is a supplement to Saylor Academy's CS 102. So you should definitely find the link below to the course and start taking the course and catch up with us. Of course, if you're watching along live, feel free to leave questions in the chat, and we'll get to those as soon as we can. But with that, I'll just hand it over here to Hannah, and we can get started.
All right, welcome everyone. This is Unit 3, and as Mike said, please do ask lots of questions in the chat, and as we go through this, I'll pause periodically to answer any questions that you all have put in the chat. So please do ask lots of questions that, helps us all learn stuff and just makes it more fun and more interesting if we are, having a conversation rather than just me sitting in an office by myself talking to my computer screen. So it makes it much more fun. So let's dive into it. Unit 3 covers what is a digital signature, covers introduction to Bitcoin transactions and how Bitcoin transactions use signatures. But what we'll focus on today is we'll really get a bit in depth on pay to public key hash transactions. And I think if we really dive into that and focus on walking through that here today, that will kind of cover, help us get a understanding of, all of these topics here that Unit 3 covers. And again, this is supplementary to Unit 3 of the course, so we're not going to cover everything that's in Unit 3, but here today we'll focus on pay to public key hash transactions. And that's really still I think the most common type of Bitcoin transaction. And it's not quite the original, but it does just call it the original form of Bitcoin transactions. So if we really grasp what's happening in P2PKH transactions, then we can, that gives us a really solid foundation for understanding, what's going on in all kinds of other transactions that are now on the network. So let's go ahead and get into that. Again, digital signatures. Hope y'all can't hear my neighbor's dog going nuts. This is a lovely graph we have here showing, some elliptic curve mathematics, graph there of that, which is quite cool. So we did in the last unit, Unit 2, talk a bit about cryptography and public and private key pairs and the different ways, the different cryptographic functions that we use in Bitcoin. And we'll come back to that a bit more and we'll focus in a bit on signatures. And at the end of this session today, we'll do a quick example where we'll go through creating a signature and validating it in Python. But we're not going to dive too heavily into the math. Again, there's description of elliptic curve mathematics and how it's used to generate public and private keys and all that good stuff that we cover in the course from the book Mastering Bitcoin. But then again, we're just going to need to be aware. We just need to be aware of what this stuff is, and that'll help us work with it. All right, we're not going to dive too much into the math. Okay. So let's start first with a bit of a history lesson. Pay to public key hash is the most common type of Bitcoin transaction, not quite the original, because at first there was pay to public key. But for some security and privacy reasons, that was pay to public key hash. Also helps compress the data that goes in the blockchain. So for a couple of those reasons, pay to public key was changed to public key hash. But I think it's helpful just to think about, pay to public key, because this is a very sort of a more simplified version. And if we can understand kind of what was the thought process is Bitcoin is this system that's built on this, public key infrastructure, right? This idea that you have this public and private key pairs, right? And everything's kind of built up upon upon that. So the idea is originally, as we walk through these transactions, you can kind of think of maybe the way Satoshi was thinking about this is like, okay, I have a public and private key pair. I'm keeping that private key private. That public key is public. And if someone wants to send me Bitcoin, they essentially send that Bitcoin to my pub key, right? And kind of lock it to my pub key. And then once that Bitcoin is locked to my pub key, the only person that can spend it is me, because I have the private key associated with that pub key and that key pair. And the only way to spend it, to have the network agree that this is a valid transaction, is if I produce a signature on that transaction that we can all validate came from the private key associated with that pub key that the Bitcoin is locked to, right? So that's basic idea of, you know, how this simplified form, or the most simple form of Bitcoin transactions work, is that we just all have these pub keys, right? And people just send Bitcoin to your pub key, and then you are the only person that can spend it from there, that can send it to someone else's pub key, because you're the only person, assuming you're the only person that has that private key, then you're the only person that can produce a signature that's necessary to create a valid transaction to send those funds out to someone else's pub key, right? So I think it's helpful to know that history, to understand that that's the basic fundamental idea, is we lock Bitcoin to pub keys, and then only the person with the corresponding private key can create a valid signature to send it to someone else's pub key, right? To lock it to someone else's pub key. That's the basic form of transactions. And then it's just gotten, you know, all kinds of different complexity and different functionality have been added to it from there, including right at the beginning when pay to public key became pay to public key hash. Again, this was instead of sending funds to just someone's pub key, you would send it to, you know, an address, which is basically a hashed and formatted version of a pub key. There's a number of different reasons for that, to make it, you know, even more difficult to sort of attempt to reverse engineer that, right? Because it's not directly the pub key, it's the hash of the pub key. Also, the different types of hashes used to help compress the data, so you have less, you know, you're taking up less space on the blockchain. Here we go. This is just what I was talking about. You have this pub key. First, you hash it with SHA-256, which, you know, is a very, very secure hashing algorithm, right? Then you hash it again with this RIPE MD160, which makes it a shorter hash, right? Then that goes through some formatting, this base 58 check encoding, excuse me, which we'll talk about later in the course, or is discussed later in the course, and then that creates this address, right? So it started with this very simple idea that you're just going to send funds to someone's pub key. They can only unlock it with their corresponding private key. But we, you know, for security reasons and, you know, data blockchain space reasons, right, added this complexity to it. But that's the basic idea. All right, now here we are. I just want to show you this so that if you come across, you know, as you're working with this tech, you're going to come across with different types of Bitcoin addresses. So you should have some familiarity with what all these things mean. Here, we're just going to be talking about this first one, pay to public key hash. That address, as it's formatted, here as it goes through this whole process, comes out at the other end looking like this, starting with a 1. The next sort of upgrade in Bitcoin transactions was pay to script hash, which is how you get multi-sig, which is all sorts of really fascinating stuff, but we're not going to talk about that today. But that address starts with a 3. After that, we had, you know, SegWit, right? And then you get this pay to witness public key hash, right? And those addresses look like this, BC1Q, right? And then the latest sort of change to Bitcoin transactions was the pay to taproot transaction, which looks like this, BC1P. Again, that's outside of the scope of what we'll talk about for today, and a lot, especially this one, is pretty new. But it's just helpful for you to keep this in mind, that, you know, Bitcoin transactions, you know, you have this formatted address, and they will look different depending on what type of address, what type of transaction that is. So you might see addresses on the Bitcoin blockchain that look like this, right? These different types of formats. Okay, so before we start walking through a pay to public key hash transactions, I'll pause in case we have any questions on that bit of history there. Mike, do we have any questions?
We don't have any questions right now. Some people saying hello in the chat. Hello there, everybody. And again, if you have any questions, feel free to go ahead and leave them down in the chat, and I will I'll let you know if any come through.
Okay, awesome. All right, let's dive into pay to public key hash transactions. And here, one of the most difficult things about trying to teach, Bitcoin and Bitcoin technology and how this all works is trying to decide where to start, right? Because there's so many different interconnected concepts and technologies and techniques, et cetera, that are all working together. And to understand it, you kind of have to understand the whole constellation of things that are, being used. But when you're teaching it, when you're trying to explain it, you kind of just have to pick a starting point, and it's difficult because everything's kind of dependent on everything else. So here what I've done is I've just picked a method for walking through this. What we're kind of going to come back and forth on some of these things and touch on things briefly and then come back around to them, because they all are interconnected and there's no clear direction to start with this concept and then lead up to that one. So we'll bounce around a bit. And I think often also because these are, this is new technology and there's lots of different components at play, and you kind of have to understand all of them to get the full picture. That sometimes it takes a number of passes at it to fully grasp it. So if you've already gone through Unit 3, or if you've read some of, Mastering Bitcoin Second Edition that we reference in the course, or watched some of the videos, you might already have an idea. But with a lot of these things, and every time I'm learning something new to Bitcoin, with Taproot stuff, like I'll read the same things over and over again until it properly settles into my head. So we'll come back and forth a few times. All right, so again, a key pair is created, right? So we're kind of going to walk through the process of a pay to public key hash transaction, right? So a key pair is created. That is a pub key and an associated private key, right? All right, the public key is hashed and formatted to create an address. Okay, we got that. Funds are locked to that address, right? So if I've gone and I've instructed my Bitcoin software to create a key pair and then take that public key and format it into an address, then let's say Mike sends me some Bitcoin, he would just broadcast to the Bitcoin network, hey, I'm taking these, tiny transaction, I'm taking these 100,000 Satoshis and I'm going to send it to this address, right? So what happens is he locks those funds, creates a locking script, broadcast that to the Bitcoin network. It gets, mined in a block. It becomes part of the blockchain. There are funds that are locked to my address, right? That is associated with my public key, or produced from my public key. All right, a transaction that spends funds from that address needs to include a signature that was produced from the private key corresponding to the pub key that the address was created from. All right, so I go through this process. I create an address. I tell Mike about my address. He sends funds to that address, locks them on the Bitcoin blockchain to that address that I've produced. But let's say I then want to send some of those funds to my friend Daniela, right? In order to send those funds that are locked to my address and then relock them to her address, I have to first unlock them. And in this, pay to public key hash type transaction, what I would do is just produce a transaction that says, hey, I'm taking this Bitcoin here and I'm sending it to this address over there. And then I would create a signature. And that signature, in order for that transaction to be valid, can only have been created by the private key corresponding to the pub key that was used to create that address, right? All right. That signature from my private key unlocks those funds so I can send them to Daniela and relock them to Daniela's address. All right, to understand
hey,
the locking
Hannah.
and unlock.
Real
Yeah.
quick, we had some questions back there. I wanted to see if you get through to see if maybe you've already answered them for people. But there, we have two questions here about basically about it seems about the concept of older addresses interacting or targeting newer addresses.
So like
and
the idea being, if I have funds locked to a pay to public key hash address, can I take those funds and send them to a pay to taproot address?
when train, oh, get more stuff in. But yeah, so the original question was, is there any special consideration when transacting with an older address type when targeting a newer type?
Okay, so yeah, I think that's kind of this question. Let's say I have funds locked at a pay to public key hash transaction, but Daniela is now sends me a pay to taproot address, right? And how would I go through that process? So we'll look a bit in a minute. We'll dive a bit more in depth with the locking and unlocking, but essentially, yeah, that wouldn't be a problem, because in that Bitcoin transaction, what I would do is I would have to provide a valid unlocking script, right, for the funds that were locked to my address. So I would have to provide that signature that satisfies that locking script. But then in the output of that transaction, where I am sending funds to Daniela's pay to taproot address, I would create a locking script that is appropriate for that address, right? And talking about locking scripts for pay to taproot addresses is like outside the scope of the course, what we're doing today. But essentially, that's not a problem. I just have to provide an unlocking script, which we'll see in a second here as we go to here. This input right here's the unlocking script. So I would have to provide an unlocking script that is appropriate for that pay to public key hash address. And then in the output, this new locking script, then I can create a locking script that's appropriate for the address where Daniela is receiving funds. I hope that helps there. Any other questions, Mike? Well, you're either on mute or there are no questions. So I will move on. All right.
Sorry about that. They can hear me.
No worries.
Yes.
Okay.
I think we should probably move on, just because there are some questions, but I think having seen the slides, they might be answered going on. So if your question isn't answered in the next couple slides, please restate it and we'll get back to it.
Gotcha. Okay, let's do that. Okay, so we've gone through this, the whole, funds are locked to my address. I have to unlock them to send them on to Daniela's address, right? All right, so to understand the locking and unlocking, let's go through inputs and outputs and the UTXO, the all-important UTXO. So let's look at this picture, which is one way to envision UTXOs. And again, this is like this circular sort of thing where we're going to talk now about UTXOs, but we might come back to it in a bit because all these concepts go together. All right. So first of all, a UTXO is an unspent transaction output. So let's go back to that example. I have created this key pair. From that pub key, I've produced an address. Mike has sent funds to that address and locked them to that address that I produced. So that is an unspent transaction output. So again, if we come back here and look at the structure of a transaction, we'll dive into depth in this in a minute. But here's this output, right? Some sort of input, and there's this output. And here, this is, funds being locked to, locked with this particular script, right? So they are locked, right? It's an output that is locked with a particular locking script, but is out on the blockchain. And in theory, it is spendable Bitcoin, right? If someone can produce the appropriate unlocking script, it is spendable, right? So this is important because so much in Bitcoin, we think about UTXOs, right? These are basically chunks of Bitcoin on the blockchain that could be spent. So let's look at here. Let's walk through this example from the Mastering Bitcoin book. This is like a whole block here. This is numbered, right? And this is another block, and this is another block, etc. So in this block, we had a whole bunch of transactions, right? So Joe here had a UTXO, but he took that output that he had and he used it to create a transaction to Alice, which creates another output, right? Then Alice took, and that happened in this block, and then Alice used that output that she had to create another transaction where she sent some funds to Bob, but some back to her, right? Bob, and so here she has this funds that she potentially could unlock and use. This is a unspent transaction output, a UTXO. Bob then goes and takes his UTXO and uses it as an input, so he spends it, but he produces two outputs, one back to him and one to Gopesh here, right? So as we look at this, we want to track, once you have an output, once that is used as an input on a transaction, it is then a spent transaction output, right? And so in the Bitcoin world, as we're thinking about a lot of this stuff, we're generally much less concerned with the spent transaction outputs than we are with the unspent transaction outputs. Like, your Bitcoin node will track all the unspent transaction outputs it can find, right? It's going to find all of them on the blockchain. It's going to track it and keep a track of those and keep an eye out for them to see if anyone wants to spend those. So a UTXO is just bits of Bitcoin that could be unlocked and transferred elsewhere, right? And you can use this picture to imagine it if you like. All of these ones in red are outputs that were then used as inputs. They are spent Bitcoin. That Bitcoin is moved on from that address. And then all these ones in green are these outputs, like funds that are locked somewhere that could potentially be spent, right? So, well, with that understanding of UTXOs, we'll kind of dive back into our whole process, walking through this transaction process. All right, we're not going to go too in depth with this at the moment because we just want to get the concept of inputs and outputs, and then in a couple of slides, we'll come back to this picture here and really walk through it in a bit more depth. But again, what's important to pick up from this slide is just the idea that all Bitcoin transactions have some inputs that are used for them, right? This was a UTXO here, right? When Mike sends me that Bitcoin and it's locked to my address, that's a UTXO. And then if I want to send Daniela some funds, I can use that UTXO as an input, and then in this Bitcoin transaction, create a new output. So this is now no longer a UTXO. It's a spent transaction output. We don't care about that anymore, as long as it's valid, right? And then what we now care about are these two outputs, which I created here, perhaps one going back to myself and then one going on to Daniela, right? And these are our new UTXOs. So we consumed one UTXO here as an input and produced these two new UTXOs as an output. This is no longer a UTXO at spent. Now we care about these two UTXOs, these two outputs, unspent transaction outputs. Okay. So every Bitcoin transaction is kind of going to go through that process. Input, output, consume a UTXO, create new UTXOs, right? Sort of that process. All right. So a couple of things about UTXOs, and then we'll pause for questions, and then we'll dive a bit more into depth on this image here, this process. All right, transaction outputs consist of two parts: an amount of Bitcoin denominated in Satoshis, the smallest unit of Bitcoin, and a cryptographic puzzle that determines the conditions required to spend that output. Okay, so if we come back and look at this, we can kind of see that's what's going on here. We have a value and we have this locking script, which we'll talk about more in a minute. All right, so this is also known as a locking script, a witness script, or a script pub key. Actually, in here, let's talk about it. This says script pub key and script sig, right? Script signature. And you can see that this is what it looks like in the Bitcoin, Bitcoin Core code. And it got this name because of this original type of transaction, which is the pay to, pub key hash, right? So with that in mind, I guess when the Bitcoin was written, I guess Satoshi was only envisioning this type of transaction, right? So script pub key, it's like saying I'm locking the Bitcoin to this public key, right? And in order to spend, that Bitcoin, you have to unlock it with the signature, right? But of course, now, because we have much more complex versions of Bitcoin transactions, that terminology isn't really entirely accurate. So I tend to use just the term locking and unlocking script, right? But witness script or script pub key, et cetera, like there's a different terminology used for this. I prefer locking and unlocking script. So that's what I use. All right, each input contains an unlocking script and refers to a previously existing UTXO. All right, the validation software will copy the unlocking script, retrieve the UTXO referenced by the inputs, and copy the locking script from that UTXO. The unlocking and locking script are then executed in sequence. Okay, so that was a lot, but we'll walk through it in a bit more depth in the coming slides in just a second. All right. When we say that a user's wallet has received Bitcoin, what we mean is that the wallet has detected on the blockchain a UTXO that can be spent with one of the keys controlled by that wallet, right? Your wallet is like scans the Bitcoin blockchain. It's like, aha, that UTXO, I think I can spend it if I want to. So that then your wallet says that's part of my balance, right? All right, thus a user's Bitcoin balance is the sum of all UTXOs that the user's wallet can spend, and which may be scattered among hundreds of transactions and hundreds of blocks, right? So the idea of telling you this here is that, you know, if you get a Bitcoin wallet and install it on your phone and open it, it's kind of going to say, here's your balance, right? And this is your wallet making things really easy for humans. That's actually not what's happening on the Bitcoin blockchain. Things are scattered. These UTXOs, right, if we back up to this picture, these UTXOs might be scattered over a number of different blocks. We can see Alice has 3 different UTXOs, right, which are scattered over, you know, all these different blocks here. And then, but this might be the current UTXO set down here. So her wallet might be aware of this UTXO, this UTXO, and this UTXO. And it looks sort of different on the blockchain than it is presented for Alice in her wallet. Okay, so now that we've talked through that, we'll dive more in depth into what's happening in this particular Bitcoin transaction. But first, if there are questions that we've not yet properly answered, we might answer them here. But Mike, if we've got any interesting ones, please let me know.
Well, we had a question about UTXO, so I hope that that helped to answer that one. You know what? Why don't we just go and I'll collate some, and if you guys have questions as we go along after this next slide, I'll be back with some.
Okay, awesome. Thank you.
Sounds like a good plan.
All right, so here we're going to, this, as you look at this, it's kind of confusing, right? First time you look at this, you're like, wait, where's the Bitcoin and what's happening and what's this V out and sequence, and I don't get what's going on here, right? And what we need to keep in mind is the Bitcoin software is always trying to preserve space in the Bitcoin blockchain, right? So we want to broadcast and record absolutely as little information as we need to, so we don't bloat the Bitcoin blockchain, right? So a lot of what's happening here is just reference to other things. For example, let's look at this input, right? And this V in, these are the inputs being used for this transaction, right? So again, if this is that Mike has sent me some Bitcoin and I want to send some of that Bitcoin on to Daniela, this might be the transaction that my wallet puts together for me, right? And it's going to say, hey, this is the inputs I'm using. This is a UTXO, which I'm going to consume and thus destroy to create new UTXOs, right? So this is the UTXO that I'm going to use. I'm not going to tell you all the information about it because that would be a duplicate. All the information about that UTXO already exists in the blockchain. So all I'm going to do is just point you to it. This, oops, I forgot that this is just an image and I can't highlight it. Maybe I will go here. Oops, hold on. There we go. Haha. Okay. So, and then maybe I can zoom in a little bit. This one, zoom in. Maybe. Okay, but Control plus. Thank you, Mike. That was it. All right. So hopefully you can see this a little bit better, but the idea is I'm just going to tell all the Bitcoin nodes that I broadcast this transaction to. I'm like, hey, I'm not going to put all the details of this UTXO here because I'm just going to tell you where to find it. You go back and look at the blockchain and you look for this transaction and you look at this specific outputs of that transaction, because we can see here, transactions can have a number of different outputs, right? So if you look at the very first output of this transaction, you're going to find the UTXO that I'm talking about and that I want to use. And so, you know, someone else's Bitcoin node, right, is going to go out and say, oh, okay, all right, I have to go find that UTXO here. It's going to find another transaction that looks very similar to this. It's going to say, right, here's the first output of that transaction. Here is the locking script. So I'm going to copy that, right? Then I'm also going to take this unlocking script. And you can see it's kind of big here. There's a lot going on, but it's going to copy this whole thing, boom. And then it's going to run those two things together. We won't talk too much in depth here about Bitcoin scripting because we cover that in depth in Unit 7. But the idea is that it takes the unlocking script, it puts it together, or it takes the locking script, it puts it together with the unlocking script, and it runs those two together and see if one can satisfy the other, right? If so, then my transaction to Daniela is valid, right? So let's look a bit at what's happening here. We'll stick to this one here. So this is complex, but hey, basically it's saying I'm locking this to this pub key, right? Again, we'll get into this in Unit 7, kind of simplified. But then it's saying, hey, I have to satisfy this big long thing here is going to be a signature, right? And we'll talk a bit more depth in signatures in a minute. And here is the pub key, right? So these look a bit different. They're all formatted a bit different. Again, Unit 7, we'll talk about that. But that's basically what's happening. So if we come back here and we look at this one, all right? Here is a more in-depth view is that locking script and that unlocking script. And we'll talk about how these are run together also in Unit 7. But basically it's saying, hey, do all these things to format this pub key, right? This hash of a pub key, right? And then I have to unlock it and spend it. I have to produce a signature that can be validated using this pub key, right? So signature that was produced with the private key corresponding with this pub key, right? And these have to match up. So I have to prove that I can produce a signature that is from the private key corresponding with this pub key, right? That's what I need to do to unlock that UTXO and send some funds onto Daniela, right? So that's roughly what's happening here. Let's go through some of this because you might be still looking around going, why is there all kinds of different things? This is script version. Again, that's for later. Lock time, that's time locks and all this stuff. Very fascinating stuff. That's for later. This VN, these are all the different inputs that we're using. It might be that I want to send Daniela more money than Mike sent me, right? I want to send her more Bitcoin than I received from Mike. So I have to use another UTXO that I got from Charlie earlier, right? And I have to put those together to then be able to have enough funds to send on to Daniela, right? So I could have a whole bunch of inputs. I could have one or many outputs, right? But here, that's what's happening. For every input, we're referencing a previous UTXO via this, and we're producing an unlocking script, which in this case is a signature, but it could be a number of different things. And we're producing an unlocking script in this sequence. Again, that's used for time lock sort of stuff, which is outside scope for today. But that's just for more complicated transactions. Okay, then let's come down and look at vout. Vout is a bit more human readable, right? We can see exactly how much we're sending, right? Maybe this is coming back to myself and this is the funds I'm sending on to Daniela. And we would know here, even though it's not expressly stated, if this is a valid transaction, then this UTXO referenced here would have to have at least this much Bitcoin in it, right? So 0.099, whatever it is, right? You add those two up Any difference between that input and those outputs is assumed to be a transaction fee, which goes to the miner, right? And again, we're putting as little data as we need to in the blockchain. So when you see this transaction, if you're trying to read this yourself as a human or you're a Bitcoin node, it's going to have to sort of create a lot of the data, like go reference other things and piece together the complete picture of what's happening here. Because again, we only give absolutely as much data as we have, do not drop more, right? So we preserve that space in the blockchain. Okay. And then looking at this V out, right? This would be output 0, this would be output 1, right? And we have a value, which is denominated in Satoshis. And then we have this script pub key, which is the locking script, right? So this in this pay to public key or pay to public key hash format, it is essentially the pub key that you're locking funds to. But because we now have much wider variety of Bitcoin transactions, it's the locking script, right? And we'll stick with that for the moment. Okay, so that was a lot. That is, let's just hold it here on this slide. That was a lot. That's a lot to sort of digest. Again, like I said, you might want to come back to this or, check out, like rewatch one of the videos from Unit 3. There's a good one there where Andreas talks through this. There's also, chapter 6 of Mastering Bitcoin goes through this, so if it doesn't all quite gel for you at the moment, just, come back tomorrow and come at it from a slightly different angle. And hopefully then that makes it all gel properly in your head. But also what helps is asking questions. Mike, do we have any questions at this point? Mike is perhaps on mute. No, he is. All right, I like that one. Cool questions. Okay, so signature verification. Who's doing the signature verification? And again, this goes back to Unit 1 where we talked about everyone needs to know about everything on the Bitcoin network. So who's verifying the signatures? Everyone. Everyone is, right? So what happens with a node is if I'm a node, right? And I'm sitting there and I'm watching this transaction, go from, Hannah to Daniela. And I'm like, is this valid, right? Every time I see a new transaction come in, I'm going to look at it. I'm going to go read the data. I'm going to go gather all the other information that I need. I'm going to, create a complete picture of that transaction. And then I'm going to validate it. So every node on the Bitcoin network is validating the signatures with every transaction, right? And it gets a bit more complicated, but every single transaction is validated by every single node on the network. So I'm going to go and I'm going to run, and we'll do this in a minute in Python so we can kind of get a feel for, of course, it's a little different in Bitcoin, a bit more complex, but we'll get a feel for doing it in Python. And so I'm going to validate it, right? And I'm going to run it through my software. And if it comes out with, hey, that signature matches, that pub key in that message, excellent, boom, that's valid. I'll then broadcast it on to other nodes, right? So if something is invalid, it's gonna, the first node to see it is gonna see it as invalid and then will refuse to broadcast it on to the rest of the network. So an invalid transaction with a bad signature isn't going to get very far on the Bitcoin network. So I hope that answers that question. Then to the question of, can you disagree? And the simple answer is no, right? Because if we had a case where there was a transaction where some nodes thought that was valid, right? Maybe that we're using, see these little things, dupe or dupe, hash 160, right? These are op codes, right? So they're like functions that the Bitcoin software runs to check on this stuff. And if someone was perhaps using an opcode that one node thought existed and another node thought was invalid and didn't exist, if that ever happened, right, you would then wind up with a split in the network, right? That would fork Bitcoin into like two different versions. So essentially, no, we can never disagree, because if we disagree, then we kind of fork the whole network. So this is part of why updating Bitcoin and changing it is so contentious and slow and difficult, because it's pretty catastrophic if we wind up with a situation where nodes disagree about what is or is not a valid transaction. And we'll talk more about that in Unit 8. The short answer is no, we never disagree. We hope. So, Mike, any more questions? No worries. All right, thanks, Mike. Okay, so hopefully now we all have a pretty good idea of what's going on with UTXOs and locking scripts and unlocking scripts and pay to pub key hash transactions and inputs and outputs, right? That's the idea, is that the goal for this session is to have you all like form that picture, that map in your head of what's the flow of what's happening here and what are the necessary components and how a node puts this data together, et cetera. So hopefully we've achieved that. If not, please do come back and watch this stuff again sometimes. I mean, for me, it usually takes like 3 passes at something. All right, I think we're going to skip this for a moment. This is just a link to go look at, I think, what I tried to find this transaction in the Bitcoin blockchain, but I think we'll move on to trying our exercise to sign and validate some data, because that's really fun. And then maybe we'll come back to poke around a Bitcoin block explorer if we get the time. So let's move on to our exercise. And what we're going to do is sign and validate some data, right? So if you're following along with this, again, we're going to do this in Python. You can install Python on your machine. I'm on a Ubuntu machine here, and so that's the examples that I'm showing. I have in Python installed on my Ubuntu machine. You can also, run this in, all kinds of different, websites that'll let you run Python in the browser, et cetera. So there's lots of different ways you can follow along with this. But importantly, what I've already done and what you'd need to do to follow along with this is make sure that Python knows to go and download this specific library. So ECDSA, elliptic curve, something signature algorithm, right? I can't remember exactly what it is, but this is the mathematical library, right, that we need to do this math, this complicated math. And I'm downloading this one because there's other ways you could do it in Python where we could do signatures and we don't need this specific library, but I'm using this one because this is the, creates the type of signatures that Bitcoin uses, right? So this SECP256K1, right? This long complicated thing. This is the type of signature that Bitcoin uses. So here, I'm just telling you how to get the library you would need if you want to work with that Bitcoin variety of signatures. Now, there are other ones, but this is the one we're talking about today. It's sort of the original. Okay, so I have this code. Hold up here. I'll show you in a second. All right, but what we're going to do first is we need to generate a key specifying which curve to use. And this is the curve, right, the type of math that we want to use to create the signature. I said it in last week, and I'll say it again today. Don't roll your own crypto, right? Don't go trying creating your own curve. Don't try and create your own math here, unless you really want to be a cryptographer, right? Then definitely do that. But if you're not going to focus on being a cryptographer and working on these algorithms, just use a well-tested, well-used common library, because if you don't, you'll wind up causing yourself a lot more trouble than you're able to fix. Or it could be, a lot more trouble than it's worth. Okay, so here we go. I have this file. I'm just going to uncomment as we go. First, we can see that we are importing this signing key, like this particular, the library to, do the math that is necessary for this particular variety of signature, right? So from this library here. Okay. Then we're going to generate a key, a signing key. So here we've been talking about public keys and private keys, but when you're talking about signatures, they're often called a signing key and a verifying key. We can just remember that the signing key is the private key and the verifying key is our public key. All right. So first thing we do is generate the signing key, right? Generate the pub key, or sorry, private key. So we always, when we're generating these key pairs, you start with the public key, or dang it, I keep getting it backwards. Let me try that one more time. When you're generating these key pairs, you always start with the private key, and then that, a public key is derived from the private key. So the first thing we do here is generate a private key or a signing key using this specific math here in that library. Then we'll go and use that to create this verifying key. So we take this signing key, run this function on it, and produce this verifying key or a pub key. All right. Now let's go, no, not that one. All right, so there are sort of three components we need to think about here, at least when verifying, is we need to have the message, the signature, and the pub key, right? So we need to create this message, right? Now, if this were a Bitcoin transaction, this lovely phrase here, not your keys, not your coins, we could replace that with an actual Bitcoin transaction with inputs and outputs, etc. But here, just for demonstration, we're just creating a string, right? A simple string, which we'll sign. And so here it's not your keys, not your coins. All right. So then once we've created this message, right? This is the creation of our message, but then we'll use the signing key, which remember is our private key, and we'll run this function on it to sign it. And that's going to produce a signature, right? And let's come back here for a moment and look at this. This is one of my favorite graphics to use when talking about this stuff. Before, we were talking about, last week, we're talking about the difference between encrypting data, signing data, and hashing data. Remember, when we are signing, we're taking the message. We're not altering the message. We're not really doing anything to that. We're just producing an additional bit of information, which is that signature, right? So when we go to validate, we're still going to take the original message. We're just going to add to it that signature, and then we're going to validate it against the pub key. Okay, so let's come back here. All right, so now we've done that. We've imported our library. We've generated the private key or the signing key. We've generated the pub key or the verifying key. We've created a message, and we have produced a signature. Now, let's print that out so we can have a look at it. So I'm going to save this. I'm going to come over here to terminal. Hopefully y'all can see that pretty well. I zoomed in a bit today. And then, there we go. I'm going to run this file, and hopefully it spits out a signature. Ta-da! It doesn't look very nice, right? Because that's readable for computers, not for humans, right? But that is our signature. Okay, so that's what we spit out on the screen. But we have all this different data. We have keys, we have the message, we have the signature. All right, so now let's go through and try to validate that this is a valid signature, right? We're going to go through and check this. And look at this, because it's Python and we're trying to sort of do all these different things. So it's kind of difficult, a little bit difficult to read it. Let's go look at the different components that we're putting in, like the different components, the different bits of data that we need to validate the signature. All right, the first thing is our message. Not your keys, not your coins, exclamation mark, right? Can't change anything about that message or it will no longer be valid. All right, then we have this bit of data, which is the signature that we just created and spit out on the screen. And then we have our verifying key or our pub key, right? So we have those three bits of data. And then we can put these all together and fancy math happens. And if they all match up, right, we can be pretty darn sure that this message was signed by the person that holds the private key associated with this pub key, this verifying key. All right. So we can do this, and then here we are. So just the functions that we've used here in Python, this isn't really going to print anything out on the screen. It's just going to throw an error if it doesn't work. All right. So I have this print statement there, and if we manage to see this as an output in terminal, then we know that that assert function has ran without throwing an error. So essentially it validated the signature. So let's save this. We'll come back here and we'll run that and let's see what happens. Ta-da! Congrats, you successfully validated the signature. Now, let's look at why this stuff is so important to Bitcoin, right? It's so important because this is how I can be assured that, Mike sent me those funds and he locked it, with that locking script to my address. The idea being that only me, the person that's hopefully the only person that's holding the private key associated with that pub key that Mike locked those funds to, only I should be able to produce a valid signature to send those funds off to Daniela or Charlie or whomever, right? Now, if this needs to be the case that only I can do that, and this message used to create that signature can't be tampered with. Otherwise, Mike could see that transaction and just alter the message to be like, actually, one of those outputs is going to come back to me, right? And anyone could do this, right? And just alter that transaction so that they're receiving that Bitcoin, or they're getting that UTXO, which they can unlock, right? Instead of Daniela getting it. So the idea being is that if we alter this message in any way, this signature cannot be validated, right? It'll throw an error, right? So let's change that. And I'm just going to change this exclamation point to a period, right? Very, very tiny change. I'm going to save that. And then we're going to go back to the terminal here. And we're going to run this again and see what happens. Boom, here we go. We got an error. Bad signature error. Signature verification failed. So this is mission accomplished for this cryptography, right? It says if I try and alter this message, because this message was the input used when we created this signature, right? If I alter this message in any fashion from what was used to create the signature, then I'm not going to be able to validate it. So this is how, for this type of transaction, this is how the Bitcoin system prevents someone from just going in and being like, nah, actually that Bitcoin is mine, send it over here, right? You can't do that because the math, the public keys, the verification, et cetera, won't line up and won't work. All right, so that hopefully was, like, I always enjoy messing with this stuff in Python. Hopefully you all can follow along with this and have a bit of fun with that as well. But at this point, we only got a few minutes left. Mike, do we have any questions? Yes, I believe that's accurate. What I remember about it is that, yeah, and I can't remember exactly what the B is, but that sounds right, because I remember when I was putting the script together, it's like, if that's not there, it's not going to work, right? That's how Python knows that this is a string that I'm passing it. Yeah. Awesome. All right. Any other questions? No?
Right now, no, we don't.
Okay, cool.
But if anyone has any questions, please feel free to put them down in the chat below. But while we do that, I'll just vamp for a minute and thank everyone for joining us. And of course, thank you, Hannah, for taking us through this so far. And of course, if you just getting here, this is, again, a supplement to Saylor Academy's course. So please find it in the link below and start taking the course. You can find the other videos also if you need to catch up. And yeah, I'm not seeing any questions coming in. That's about, oh, never mind. Every time I say it.
We get another one. All right, what do we got?
Is there any reason to transition UTXOs from one style of address to a newer one?
Okay, so if you're holding Bitcoin in, let's say, pay to pub key hash addresses? Would you want maybe to then hold that Bitcoin in pay to taproot addresses? And the answer is yeah, totally. Or how about, maybe you want to move that from pay to public key hash addresses to like SegWit addresses, maybe because you're then going to go and use that money on the Bitcoin Lightning Network, et cetera. And there's all sorts of specific use cases we could get into. Maybe there's some functionality you want to use that requires taproot. So you would want to move your funds to taproot addresses. So yes, there's definitely reasons why you would want to use one type of address over the other, but I don't think you really have to worry about like, if I'm storing Bitcoin in pay to public key hash, do I ever need to like move it or whatever? It's like, nah, not really. Because if you're storing it here in this, maybe older type of address, but you're going to want to use this service over here that requires a newer type of address, then, whenever it is you get around to doing that, just you would create a transaction that as you went, like if you wanted to open a lightning channel or something, when you moved those funds, you would take these UTXOs as an input, and those outputs would just be of the new variety. It would be a SegWit address that you would use as the output to open that lightning channel. So functionally, I'd say you don't really need to concern yourself with what type of address format your Bitcoin is currently stored in. It's just whenever you want to do a new feature, you would have to have a wallet that was, speaks that language, right? Is enabled with that feature. And then as you move funds over to go use that feature, that transaction would just take an input from an old address type and spit it out, lock it to a new address type. So kind of, but don't worry about it, I think is the answer there.
Excellent. We got a thank you there in the chat. And I guess the final question we'll go out on here real quick is someone wondering, they won't have to be writing code to create signatures, will they? Or they will be happy?
Yes and no. So this, hold on, let's go back here. This is like the level of code that you might have to write, right? Unless you really want to get in depth, you really want to be like a cryptographer or a protocol engineer, then you would be. But if you're just like, a lot of the work that I've done is just sort of integrating Bitcoin functionality into other systems, like working with Bitcoin, not really being a Bitcoin protocol engineer. And then in this case, like generally it's going to be finding the appropriate library, making sure it's a really good, solid library, and asking Google or referencing the documentation to find the appropriate functions to use in that library. Like what we see here is kind of, in general, unless you're going to be a cryptographer or a protocol engineer, this is sort of the level on which you'll have to actually work with that math.
Okay, excellent. Thanks a lot. And I think with that, we'll call this one. And again, just a big thank you to Hannah for taking us through this, and a big thank you to everyone for joining us. We will see you for Unit 4, same time next week. And if you are watching this later and you have any questions, leave them in the comments. Thank you again, everybody. We'll see you next week.
All right.